Well, welcome back. We are in week 3. So as we get started, let's do a quick review of what we've learned so far. In week 1, we did a review of basic statistics, all of the things that you forgot since our initial statistics course. And then in week 2, we learned about statistical software, what's going to do all the mathematical heavy lifting for us when we get ready to actually run some tests. So we're moving toward doing hypothesis testing, where we're going to be using those basics of statistics that we learned about in a way that allows us to make some inferences about samples and populations. Well, before we do that, we ought to review the steps of hypothesis testing so I can remind you a little bit about that and show you how to do it the right way. And by right way, I mean the way that I do it. So this is actually not the only way that this can be done, but I'm going to use the same 5 steps for all the tests that I teach you. So I want you to be familiar with what I'm doing, and then every time we learn a new test, we'll walk through exactly the same steps, so you'll always know that you're getting everything completed and you're not missing any of those steps. So let's jump into an introduction to hypothesis testing. Among the things that we learned about in week 1 was that anytime you draw a sample from a population, that what is true of that population should be true of the sample drawn from that population. Meaning that if the mean of the population is 5'10", then when you draw a sample from that population, you expect that the sample is going to have a mean of 5'10". Any sample drawn from a population should have the same characteristics as the population from which it was drawn. But here's the thing. It doesn't usually work that way. Anytime you draw a sample from a population, the sample mean is probably going to be close to the population mean, but it'll always be off by a little bit. If you do multiple samples, most of them are going to come in really close to that population mean. But there'll always be some that are a little squirrely, that end up being far from the population mean, or at least far from the means of all those other samples that you drew, for reasons that have nothing to do with anything other than just random chance. So here's the thing. Even though we expect that the sample mean and the population mean will be the same, we know that the sample mean and the population mean will be different. However, most of those differences are not due to anything changing in the sample in reality. It's just random chance that explains why the means are different. So anytime you have a difference between a sample and a population mean, you need to explain why that difference exists. And most of the time it's going to be random chance. That explains why the sample mean and the population mean are different. However, and this is especially true if you do some kind of treatment, sometimes the sample mean and the population mean are different because there was an effect, that the drug that you're testing actually worked. There's still some random chance, but the biggest reason for the difference between those two means is the effect. The drug actually worked. The intervention was successful. And the way that we're going to make that determination, when we find a mean that's different from the population mean, is we're going to use probability to determine how likely is it that we got just a squirrely mean that's different from the population mean by random chance versus how likely it would be to get the same mean if we have an effect. And that is the basics of hypothesis testing. So we are going to learn about hypothesis testing using a fun example about baby weight. So how much do babies weigh? Any guesses on how much do babies weigh?
Probably around
5 pounds. That sounds right to me. Any other guys want to guess? You got any guesses on just, are they 5 pounds? Like
7 pounds.
7 pounds? Sounds pretty good. All right. Occasionally, people will be talking and someone will describe a baby being born and someone will say, wow, that was a really big baby. And then sometimes it'll be like maybe an underweight baby. So what would be the range in which you would say we have like a low number, underweight, versus a large number? Like what would be still in the range of normal, but big? Let's start with underweight. What would be a low weight for a baby? 2 pounds. That seems pretty small. Okay, so 2 pounds is going to be our low. What's the high? 20 pounds. So anywhere between 2 and 20 pounds is normal. No? Okay. Well, I did do a little research into this, and here's what I found from the World Health Organization, that in developed countries, the average newborn weighs 7.5 pounds, with a range between 6 and 10.1 pounds. So those are the numbers we're going to use. The world average, the population average, is 7.5 pounds. But then you read something on the internet about a baby who was born in Siberia who weighed 17 pounds 1 ounce. It's a true story. I found it on the internet. Hey, there's pictures. You can't fake those. So this got to be true. I actually do believe that it is true. It came from the Reuters news service. And what happens is you get a little curious about this, and you start thinking, is there something different about Siberia? They're part of the world population, but is there something about that particular little sliver of the world that's different from most places? And so you dig into this a little more, and you discover, and at this point I'm just making things up, you discover that in Siberia, the average baby weight is 11 pounds. Now that is different than the world average of 7.5. But is it really different? Is it significantly different? Is it statistically significantly different than the world population mean? We want to answer the question, how well does my Siberian sample mean represent the world population mean? Clearly, it is different, but is it different because of random chance, or is it different because of an effect? Now, at this point, we're not speculating on what that effect might be. Was it something in the water, or is it nuclear fallout, or some other reason? We're not saying what that is yet. We're just wanting to know, given what we've discovered about that 11-pound average versus the 7.5-pound average, is that likely to happen by chance, or might there be some other reason why that difference would exist? We're then going to use 5 steps as we walk through hypothesis testing so that we are always doing the same logical steps and we're not missing anything along the way. These are the steps that I use, and I break it down into 5, but I know that there are other textbooks that use 5, and their 5 are a little different than the 5 that I'm using. Or I've seen it as 4, I've seen it as 3 steps. So one textbook tried to do it with 2 steps, which just seems a little too few. And then others that do 6 steps. Here's the point. Everything I'm going to teach you is exactly the same as what all those other textbooks teach. It's really just how you group the steps. So this is the way that works best for me. It's going to teach you, if you know this, you know a way of doing hypothesis testing, and that's really what's important for our lecture today. Right. Step number 1, select the appropriate test. We're going to decide what test to use, and when we do that, we're going to look at the assumptions for that test. Every test comes with built-in assumptions, like this has to be true about the data in order to use this test. We want to check those assumptions, and then we'll select the test that we're going to run. Next, we're going to establish the null and alternative hypothesis. We're going to establish a testable prediction about what we think is the case about the data that we have. Number 3 is we're going to select a criterion for statistical significance. And typically, this is going to be p less than 0.05. Step number 4 is where we really have fun. That's where we actually calculate the statistic using statistical software. And we drop our data into Excel or R or JASP or SPSS, and we actually run the test. Now, number 5, we interpret the results and write up the findings. We look at the results that we got from our statistical software, and we make a determination, Is that difference better explained by random chance or by an effect? For step one, we choose the appropriate statistic. And there are a few things that we should consider as we're making this choice. This is actually going to be the simplest step of all of them that we're going to do. We're going to look at the data and we're going to choose our test based upon, are we looking for differences or are we looking for relationships in the data? Do we want to find whether there are two group means that are different from each other? Or do we want to find how two variables are related to one another? If we have group means, are those two separate groups, each of which has a mean that we're going to compare? Or is maybe that the same group that's been measured once, twice, three times, like pre-test, post-test, follow-up? Or maybe we have some scale level data, we're going to do correlations or regression. The decisions are going to be made based upon the level of the data. If we have categorical data for our independent and dependent variable, we're going to do cross-tabulation counts. If we have one categorical variable and a scale variable, now we can do t-tests and ANOVAs. If we have two or more scale variables, we'll do correlation or we'll do regression. Or maybe we have categorical and scale variables and we're going to do something more complex. We have a categorical predictor and a scale outcome, or scale predictors and a categorical outcome. This process of determining the level of the data and what test is called exploratory data analysis. I just want to make sure all the assumptions are met and that I can run the test that I want to run. So I said this was going to be the simplest step, but it sounds pretty complex because there's lots of tests to know, lots of things to check on. So why is this so simple? Because I'm going to be teaching you a new test every week, sometimes two, maybe three, but I'm going to be teaching you a new test every week. And as I teach you, when we get to step one and I ask, what is the appropriate statistic? The answer is always going to be whatever test I'm teaching you about right now. So it's going to be really simple. Well, that's true for the teaching, and that's also going to be true for the assignment for this week, because you'll just be using the test we learned about. Now, when we get to the test at the end of a 4-week block, then you'll be choosing from all the tests we learned about in that block. And when we get to the final, then it'll be wide open. So you'll want to pay attention to how these tests are structured so that you'll have that statistical toolbox in your brain so you'll know what things are available to you and what test you would choose for a given level of data. Going back to our baby weight example, we have some information drawn from a sample. We'll say that there were 30 babies in our sample. Their mean was 11 pounds. We want to ask the question whether that 11-pound average is the same as the world population average of 7.5, or whether that sample of 11 represents some other as yet unknown population defined by some kind of an effect. And with that setting, we're able to do something like a z-test or a t-test. Step number 2 is to define the null and the alternative hypothesis. If we're going to do a test of whether baby weight is different in Siberia versus everywhere else in the world, you would think we'd start with a hypothesis like baby weights are different in Siberia. But that is not how we're going to begin. We're going to begin with that simple idea that I even started this lecture with, that anytime you draw a sample from a population, what is true of that sample should be true of the population from which it was drawn. That a sample drawn from a population should have the same characteristics as the population. So we are going to assume that the sample mean and the population mean are the same. And this is called our null hypothesis, our hypothesis of no difference, that our sample mean of 11 is really no different than the population mean of 7.5. There's just some random chance that explains that observed difference. Now, the reason we start with this type of hypothesis, this null hypothesis, is it is falsifiable. It is something that we can demonstrate to be false, and in doing so, we can show the probability of finding this type of result if the null hypothesis was true. And it is so unlikely we would get this result if the null hypothesis was true, we're going to conclude that, in fact, we're going to reject the null hypothesis. We're going to accept the alternative explanation. Our null hypothesis states that there is no difference between the experimental or the sample mean and the control or the population mean. And we could write this in different ways, all of them saying no difference. For instance, there will be no difference between the scores of deaf rats and the hearing rats. Or the scores this year will be the same as the scores from last year. If they are the same, that means there is no difference. Or I might just say the men's scores will be no different than the women's scores. If I put into words the null hypothesis for our example, I would write it this way. The average weight of babies born in Siberia will be no different than the world average of 7.5 pounds. But I can express this in numbers as well. My null hypothesis is always going to begin with H sub 0. H sub 0, the no difference null hypothesis, followed by colon. So the null hypothesis would be H sub 0 colon mu equals 7.5. You remember mu is a population mean. So what we're saying is this sample is drawn from a population that has a mean of 7.5. The alternative hypothesis says that the experimental sample will be different than the population. The deaf rats will have a better sense of smell than the hearing rats. The drunk people will make fewer driving mistakes than the cell phone users, which was something that I found on the Mythbusters show, the old one, where they actually tested a group of people, same group, and in one case they had alcohol to drink, and then in another case they were talking on a cell phone or texting on a cell phone as they're driving through a closed course. This is all done off of public roads and on a back lot. And in fact, they found that the distraction caused by the cell phone actually led to more problems in the driving than being legally drunk. Something to keep in mind for texting and driving. There's a third example. The number of lightning strikes on golfers will be different than the number of lightning strikes on swimmers. Now, if we're going to put our alternative hypothesis into words for our baby weight example, we'd probably write it like this. The average weight of babies born in Siberia will be different than the world average of 7.5 pounds. And if you go back to the null hypothesis, you'll notice that these two are almost exactly the same. One says will be different. The null hypothesis says will not be different. So we have two hypotheses worded almost exactly the same, and the reason why I'm doing that is I don't want any confusion. I don't want to use slightly different wording in one than the other. I want them to be exactly the same so that you can clearly tell how those two statements differ from one another. The way that I would write out my alternative hypothesis in numbers is H sub 1 colon mu does not equal 7.5. Or this sample is drawn from a population that does not have a mean of 7.5. The null hypothesis I will always write as H sub 0. For the alternative, though, you do have some flexibility. I use the convention of the alternative hypothesis being H sub 1. And if I have a second, I would write that as H sub 2. And I like that because it gives me a lot of flexibility for the way that I number. You will also see the alternative written as H sub A for alternative, or you could have an H sub B. I don't prefer that, but when you see that, they're referring to exactly the same thing. H sub 1, H sub A, both of those are alternative hypotheses. you can establish a direction for your alternative hypothesis. You can establish whether the mean will increase or decrease. These are called directional hypotheses. A directional alternative hypothesis states the direction of change. The sample mean will be higher than the population mean. Babies will weigh more. Or the sample mean will be lower than the population mean. I'm specifying a change in one direction or the other. Now, when I do that, I'm going to have to write my null and alternative hypothesis slightly differently to represent that one-tail hypothesis. It's called one-tail because when I look at my bell-shaped curve, I'm interested in only changes in one direction. So for instance, with this one-tail left curve, I'm interested in changes only where the mean decreases. And in this example with the one-tail right, I'm interested in only changes where the mean increases. So one tail goes in one direction. A non-directional hypothesis would be like the one that we began with, where I said will be different. That I'm saying different, I'm not saying higher, not saying lower, just saying there will be a difference between the sample mean and the population mean. Changes in either direction would be useful. And I want to know about changes for an increase or for a decrease. When you have two tails, it can go in two directions. Using our baby weight example, here's how we would work out this step. Our null hypothesis would be h sub 0, mu equals 7.5. The sample drawn from a population with a mean of 7.5. The average weight of babies born in Siberia will be no different than the world average of 7.5 pounds. The alternative to that would be h sub 1 colon mu does not equal 7.5. Or the average weight of babies born in Siberia will be different than the world average of 7.5 pounds. Now we're ready to select a criterion for significance. And this is where we get into that p less than 0.05. So the first thing I need to tell you is that p less than 0.05 is not magic. There is nothing about that 5% level that has any significance other than it's one that we have always used, and it's a very easily understood criteria. It's very common. Now here's the thing about p less than 0.05. There are multiple ways of interpreting this level of significance. The first is I could use that p less than 0.05 to establish a critical value, and I can then compare my test value to the critical value to see if the test value exceeds the critical value. The second approach would be looking at a probability that is created by Excel or by our statistical software and seeing whether that probability is less than 0.05. And the third would be to look at my confidence interval, my 95% confidence interval, and determining whether the null hypothesis value is inside of that interval. There's a lot to take in there. So let's walk through each of those individually so we know how we could use this p less than 0.05. The first is exceeding a critical value. Think of a critical value as a fence. And what this fence is fencing out is 5% of all the scores under the bell curve. If we have a two-tailed test, then 5% is split into two. We have 2.5% in the upper tail, 2.5% in the lower tail. If we have a one-tail test, then all of that 5% is contained in either the lower tail or the upper tail. We will look up our critical value in a table, or we'll use software to generate that critical value. Anytime we get a test value that exceeds the critical value, it's in the region of rejection, we'll say it is statistically significant. Now that's a statistical way of thinking about that, but let me see if I can do better. Let's take a different, more Ozarkian example. Ever heard of cow tipping? So maybe you're from, I don't know, Kansas City, St. Louis. You're new to the Ozarks, and some of your friends say one evening, "Hey, let's go cow tipping." And what that means is we're going to sneak into a farmer's field late at night while the cows are asleep, because cows sleep standing up. And we're going to sneak up on a cow, and we're going to push it over, because that'll be a lot of fun. Okay, please don't mess with the cows and don't try to tip them over. And by the way, cows they're really big animals. They have a fairly stable center of gravity. They're difficult to push over. And here's the thing. A lot of times when your friends are trying to convince you to go cow tipping, it's because they're setting you up. In fact, if you've seen the movie Cars, you've seen something very similar to this, where Mater convinces the Lightning McQueen to go tractor tipping. And what happens is they wake up some big red combines. If you go cow tipping, maybe you'll encounter not a cow, but a bull. Now, if you've jumped over this fence, you've sneaked up on what you thought was a cow, and you try to push over a bull, you'll discover that bulls do not like to be awakened, probably any more than you would. And they can get mad, and they are very big. And so you need to get away from the cow. You need to get over the fence. Okay. Now, here's the thing. There's a fence on one side of the field, and even if you're right up next to that fence, you're still inside the fence with the bull. It is only if you are over that fence that you are safe. And there's another fence on the other side of the field that if you're next to that fence, you are still inside the fence with the bull. You must be over the fence to be safe. And this analogy is we are going to set two fences, set by a criteria of 0.05. If the value that we calculate is 0.058, that's not over the fence. It's got to be less than 0.05. It's got to be 0.05 or 0.049 or 0.03. It has to be less than 0.05. It has to be over the fence. And this is true for either positive or negative changes. Any changes within those fences, those are not statistically significant. You're still inside the fence. When you're doing a one-tailed test, we're putting all of the scores on one end of the bell curve. So you have all 5% packed down here. And you'll notice these dotted lines, those indicate where the two-tail fences would be if we're doing a two-tail test. And I calculate this value down here, which would be over that lower fence. But this is still non-significant. When you are doing a one-tailed test, only changes in the predicted direction can be statistically significant. Why is that? Because there are some times where only one direction of change is important. We're testing a drug to see if this drug increases alertness. If the drug increases alertness, statistically significantly, we might say that drug is effective. But if it does not change alertness, or worse, makes you more drowsy, there are no changes in that direction that are useful to us. If we're looking for a drug to decrease blood pressure, and it makes blood pressure go up, there are no changes in that direction that are helpful. So when we use a one-tail test, only changes in the predicted direction can be statistically significant. The second way that we could interpret p less than 0.05 is just look at a probability value that's created by our statistical software and just interpret it. Is it less than 0.05? Now that seems easy enough until you start dealing with the numbers. We're going to call 0.05, that would be equivalent to a nickel. In medical research, we might use 0.01, that'd be like a penny, or political polling where the costs of failure don't matter quite as much. We could use more like a dime. So think about probability, which of course runs from 0 to 1. Think of it like a dollar. And then think of the probabilities as dollars and cents. In other words, p less than 0.05 would be a number less than a nickel. So when you run your test and you get a significance value for a two-tailed test of 0.32, just convert that to 32 cents. Is that less than a nickel? It's not. It's greater than. Not significant. When you get a value like 0.022, move the decimal, convert it to dollars and cents, 2 cents. Is that less than a nickel? Yes, it is. Sometimes, depending on the software that you're using, you may get a significance value of 0.000. That looks like a probability of 0, but it's not. It's just a really small probability, and there's a difference between vanishingly small probabilities and a true probability of 0. So you would never write p equals 0. You would write p less than 0.001. Anytime you get the triple zeros, just report it as less than 0.001. Another way of thinking about this would be the probability gives us the amount of evidence against the null hypothesis. So a probability of 0.05 is really the same as 0.051 or 0.059. They're really providing the same level of evidence against the null hypothesis. And so we might be interpreting our numbers this way. If the probability is less than 0.01, less than a penny, that is strong evidence to support the alternative hypothesis, and is strong evidence against the null hypothesis. Between 0.01 and 0.05, strong evidence. 0.05 to 0.1, weak evidence. And greater than 0.10, certainly insufficient evidence to support the null hypothesis. Probably the best explanation for the difference would be random chance. The third way that we can interpret p less than 0.05 is by looking at the range of values into which a mean is likely to fall 95% of the time. This could be a confidence interval around the mean, the actual number, or it could be a confidence interval around a mean difference. So what is that? A mean difference. Remember our starting point with our null hypothesis, the mean of the sample was the same as the mean of the population. The mean difference should be 0. So we're interested in whether an interval that is created for us by the statistical software contains either the null hypothesis value or 0 if we're looking at mean differences. Let me show you what this would look like. In this example, I have a 95% confidence interval around the mean. So this is the actual value of the mean. We are using a null hypothesis that the mean is 36. Our 95% confidence interval runs from 35.5 to 31.5. You can see that. Notice that that error bar does not capture the mean of 36. Here's a different example. This time, my null hypothesis is mu equals 34. I have that confidence interval of 35.5 to 31.5. You see how now the confidence interval captures the null hypothesis value? The null hypothesis value is inside the interval. This is kind of like that being inside the fence idea. Anytime you look at that range of scores and it includes your null hypothesis value, no different. They are the same. Only when your mean is outside of that range of scores would we say that it is statistically significant. That would be for a mean. If we were using mean differences, it would look more like this. We have the means of 2 samples. I've added some shading so you can see the range for this second sample. And what you see is that shading includes the mean of the first sample. So they are not different enough that we can say they are statistically significantly different. They're just statistically the same. A different example, notice how this range with the shading does not capture the mean of the second, or rather of the first group, they are significantly different. So does the interval capture the mean of the other group? And if not, they're different. But if the interval includes your null hypothesis value, then they are the same. They are not statistically different. Now here's the takeaway. All of these measures will agree with each other. They're all based on p less than 0.05. 3 different ways of looking at the data. Sometimes it just depends on what you have available with your data in your statistical software. Sometimes it's easier just to get a test value, compare it to a critical value. So that's what we go with. But all 3 of these are legitimate. Now this is an example of output for an independent samples t-test. For this test with 14 degrees of freedom, my critical value is 2.1. And you'll see that my t is 1.5. The test value is 1.5, the fence, 2.1. Do you see how we haven't made it to the fence yet? We're not over the fence. The probability, 0.13. Convert that to dollars and cents, 13 cents. Is that less than a nickel? It's not. So it's not less than a nickel, it's not statistically significant. Over here, the confidence interval of the difference, mean difference should be 0. Notice how one number is negative, the other number is positive. That crosses 0. So when I have one negative, one positive, crossing over 0, it includes 0. 0 is captured, it's not over the fence. All of these tell us the same thing. There is no difference between these 2 groups. In the second example, I would interpret the t-value with 7 degrees of freedom. The critical value is 2.3. Here my t-value is 2.7. See how 2.7 has jumped over the fence, set at 2.3. My probability, 0.02, 2 cents, less than a nickel. It's different. My confidence interval, both of them are positive, which means it does not cross 0. These are all telling me the same thing. There is a statistically significant difference between these 2 numbers. Returning to our baby weight example for step 3, we're going to set our alpha at 0.05. We'll use a 2-tailed test. Changes in either direction would be beneficial or useful to know about. We have 30 babies in our sample, and we can look up in a table a critical value for a t-test with 29 degrees of freedom. The degrees of freedom is n minus 1. That critical value is either a positive or negative 2.045. If we get a t-test value from our test that we're about to run that exceeds, is over the fence of 2.045, it is different. It is outside of that range, statistically significantly different. And now we get to have fun. Step 4, calculate the statistics. This is where we get our statistical software. We may be using Excel or JASP or R or SPSS or this one, which is Jamovi. JASP and Jamovi are very, very similar. Here's why. Both of them started as the same project. They started at the University of Amsterdam. The JASP folks, the core JASP team, was interested in developing some software that could also be used for Bayesian statistics. I mentioned that in our previous lecture. Jamovi, that team split from the JASP team, and they went a direction where they're really focusing on and really I think what they're trying to do is replace SPSS. So they have really developed, and oftentimes even before JASP had the functionality, some excellent functionality with Jamovi. I'm teaching you how to use JASP because it's the one that I've used most extensively, but I keep both of these on my computer. I've used them enough that I know what they do well. But here's the thing. If you ever download Jamovi, you will be very comfortable with it. It will work almost exactly the same. You will not have any difficulty. You'll say, wow, this looks a whole lot like JASP. Yeah, they start as the same. They've split and gone a little different direction, open source software, you can do that, and they will work in very, very similar ways. I'm going to teach you one, and then you'll be able to use the other one as well. Regardless of which software we use, we're going to get at least one of these three. We're going to get some kind of test statistic, the t-test, the f-test, the chi-square test. We're going to get a p-value associated with that test statistic. We'll get confidence intervals. Sometimes you have to ask for confidence intervals. They may not be given to you just automatically. And we'll get a measure of effect size, which I also want you to report. So we're going to find, and using JASP, we'll ask for all of these. We're going to get these results and we'll write them up. Here's one way that I might write up those type of results right here at the bottom with our t with 29 degrees of freedom. Okay. I run the statistics, and now for step 5, I interpret. What did I find? Let me make it all make sense to you. You may remember that example that I used with the raw data. And I said, we need to prepare it so that we can serve it up. I don't want to just publish the information that comes out of the statistical software. I want to serve it up so you can see what happened. I want to explain it. So here's what I might do. I want to start with making a decision about whether or not there was statistical significance. The null hypothesis, the one that we are testing, says there is no difference. The sample should be the same as the population from which that sample was drawn. If you reject the null hypothesis, if you reject the idea that there is no difference, then you are saying that there is a difference. If you reject the null that says there's no difference, you're saying that there is a difference. You are accepting the alternative hypothesis. We'll say the difference is statistically significant. The difference was not due to chance. The difference was due to an effect. So we're testing a hypothesis and making the determination whether the difference that we observed was due to chance or an effect. If we reject the null, we're saying that it was not chance, it was an effect. So when do you reject the null hypothesis? You look at the sample mean, and it is over the fence, the critical value. It is in the critical region, which is also called the region of rejection. If you look at a significance value, and it is less than 0.05, you reject the null hypothesis. If you look at your confidence interval, you're looking for a mean difference, and that mean difference does not include 0, reject the null hypothesis. We can reject the null hypothesis, but we never accept the null hypothesis. Why is that? Because at the very beginning, I told you that anytime we draw samples from populations and we expect that they're going to be the same, they're always different. But what does the null hypothesis say? No difference. We know from the outset that the null hypothesis is a lie. We know that there will be some kind of difference if we take it out to enough decimal places. So we never accept the null hypothesis that there's no difference. We fail to reject the null hypothesis. Going back to our baby weight decision, how would we interpret our findings? Here is my bell-shaped curve. I have an x-axis on which I've placed some numbers. These represent means. In the middle is the mean of 7.5. I create a fence on the lower end. That critical value to the left represents a standard deviation of negative 2.048. That's part of our critical value, which corresponds to a number on the number line of 4.905, or an alpha of 0.05. On the right, the critical value is a positive 2.048, which corresponds to a value on the number line of 10.10. Again, alpha equals 0.05. But here is that number 11 sample mean. The sample mean is 11. We can see that is over this right fence, which means that there is a statistically significant difference. If we write this up, we would say that less than 5 times in 100 would we select a sample mean of 11 by chance if the sample and the population were really the same. Now that I have interpreted the findings, I will write up the findings in APA style. So anytime you see a slide that looks like this, that's APA style. And I might say, the study was conducted to determine whether infants born in Siberia differed in weight from the world population average of 7.5 pounds. That's the study that I did. A one-sample t-test was used with a sample of 30 Siberian babies. The mean and the standard deviation are reported. Now notice that I'm reporting the mean as M and the standard deviation as SD. The reason that I'm doing that is because it is difficult to make an X bar in most, like Microsoft Word, and it can also affect publication. So APA style just says reported as a capital M for means, and that would be the same for population means, sample means, which report everything as capital M. Babies born in Siberia weighed statistically significantly more on average than the world average, and that was how I would write up those findings. And then there's my effect size of 0.88. It's a big effect, and yeah, we found a statistically significant difference. Now, we've made a decision about the data, but there's one more important thing that we should consider, and that is, did we make a mistake? Anytime you reject the null hypothesis or fail to reject the null hypothesis, you could be wrong. You could make a mistake. And these mistakes are called type 1 or type 2 errors. You could reject the null hypothesis when it's true, or you could fail to reject the null when it's false. Here is how our textbook and many textbooks spell this out. They'll give you a chart that looks like this, where we have the true state of the world, and we have the sample outcome, which would either be accepting or rejecting the null hypothesis. We know that thing about the null hypothesis and accepting, but those are the terminologies they often use. So if you accept the null hypothesis and the null hypothesis is true, that's correct. But if the null hypothesis is false and you accept it, that's a type 2 error. Well, here's the thing. This is really difficult to follow because it's this rejecting the null, there's no it's difficult. So I came up with, I think, a better way of explaining that. This uses an example of pregnancy testing. At any time in history, everybody in the world is either pregnant or not pregnant. You can't be both, you can't be neither, you gotta be one or the other. So you could take a pregnancy test, and it's going to give you one of two outcomes. It's going to say that you're pregnant, or it's going to say that you're not pregnant. This gives us 4 possibilities. Possibility number 1 is you're not pregnant. The test says that you're not pregnant. That is a correct result. On the other hand, if you are pregnant and the test says that you are pregnant, that is also a correct result. There are 2 errors that could occur, however. One would be if you were not pregnant, but the test said that you were pregnant, that's a false positive, saying something is true when it is not. On the other hand, if you are pregnant, you take this pregnancy test, it reports negative, that's a type 2 error, a false negative. It missed an effect that was really there. Type 1 errors can be serious because they're really easy to spot. Like, for instance, if you publish an article that says ecstasy promotes death of brain tissue, as was published in a journal, and then other researchers replicate your study and they say, we've been studying this drug for years and we've never seen these kind of results in the lab rats that you've just reported. And then you go back and you look at the vials and you find out that, uh-oh, there was a shipment error. The vials that were sent to you as ecstasy were actually methamphetamine. And that's why you're seeing the damage to the brain cells that everyone associates with methamphetamines. That's a problem. Now you've got to retract your article. You've got to say, I was wrong. And that's not fun. It can also damage your career if you publish false findings. So type 1 errors can be really serious. We want to avoid false positives, saying something is true when it's not. But we also want to avoid type 2 errors. Type 2 errors are missing an effect that's really there. You are studying a series of drugs, and you're looking for a drug that could be effective for certain forms of cancer. And so you're running multiple drugs on multiple different cell cultures. And what happens is you're using too small of a sample size, and maybe you're not doing the stats right. And what happens, you end up missing a drug that really is effective for a very specific, very rare form of cancer. Well, the problem is that that form of cancer, maybe that's something that you develop, maybe something a friend or a loved one develops, and you've missed this drug. This drug is not on the market when it should be. So type 2 errors can also be serious. Here's how you keep them, how you separate them, tell them apart. Type 1 errors occur when you say that something is true when it is not, that you say there is an effect when there is not. That sounds a lot like lying. So think about Pinocchio. And what happens when Pinocchio tells a lie? His nose grows. So think about Pinocchio's nose as a type 1 error. A type 2 error occurs when you miss an effect that's really there. So the old English parochial schools where if you were not paying attention and you were not answering your lessons correctly, they might set you up in the corner with a dunce cap. So think of the shape of that as like a V shape. That is a type 2 error. There was an effect and you missed it, you big dummy. So type 1 and type 2. Type 1 is lying, saying something's true when it's not, saying there is an effect when there's not. And type 2, missing something that is really there. So now when you see something like this in a textbook, you'll have a little easier time in interpreting that. That's all we have for this week. Thank you for being here, and I'll see you guys on Thursday.